So in this video, I'm going to talk about the electric field. And I'm going to start by talking about where we left off last time, where we had a bunch of charges, and we basically calculated the force on one of the charges by looking at the superposition of forces from the other charges in the system. So basically, let's imagine we have these four charges here, Q1, 2, 3, and 4, and we wanted to calculate the force on charge 4, which is at a point P here. And so the way we did it is we said, okay, well, the force on charge 4 is equal to the force that charge 1 exerts on 4, plus the charge that 2 exerts on 4, plus the charge that plus the force that charge 3 exerts on 4. Right? So basically, it's this vector sum using this principle of superposition that we discussed. And if we wanted to write this out more explicitly, this would basically be the Coulomb's law form for this force here, and then this one, the middle one for F4 on 2, and the third one for F4 on 3. All right, so that's all well and good, but what if we decide we want to change the value of Q4? Okay? So the problem there is that, if we just do it exactly like we've written up here, then what you have to do is basically you have to redo the calculation, right? You basically have to go in on each one of these terms and basically, plug in the numbers again for each one of these three terms, and that's going to be a pain to do. So what I can do then is instead, we can do something a little bit smarter than that. So if I look at how the force on 4 is written, I'll notice here that Q4 appears in every one of these terms in the sum. So I can in fact factor Q4 out of this sum. And then, I can write these terms again. So the way I've written this now is a little bit smarter, right? So I've written out these other terms here, and now Q4 is factored out. So if I decided I wanted to change Q4 from, 10 to the minus 6 coulombs to 3 times 10 to the minus 4 coulombs, or, whatever you decided to, you wouldn't have to, all this stuff here doesn't change, right? All you have to do is basically change the value in front here. So basically, what we'll call this stuff here, and you'll notice this is a vector because we've got these r hats for the different vector pairs here. Basically, this is just the electric field. Okay, and this is the electric field at point P because Q4 happens to be at P, but maybe we'll decide to change Q4 with some other charge. So I'm not gonna, call this E at 4. I'll call it, E at P because it's really associated with that particular position in space. It's not really associated with that particular charge anymore, right? Because we're writing it in such a way that if we swap Q4 out with some other value, we always get the force for that charge that we've swapped out. So what we can do is really define the electric field E as being equal to the force at some particular point that, in this case it's point P, but the force at some particular point that's experienced by some test charge Q that you place at that position, okay? So this is basically how we define it. So if we basically imagine we had some configuration of charges like these 3 charges here, we stuck some little test charge here, and we basically said that, we looked at what force was exerted on this test charge by these 3 other charges, and then we divided out the force by the value of that test charge, we would get an electric field. And so the electric field is independent of whatever test charge I put here. So basically, the electric field is basically the electric force per unit charge. So more generally speaking, if we had n charges, we could write the force that one charge, let's say charge J, would experience would basically be equal to the sum over all the charges in the system that are except for itself. So we wouldn't look at the force on itself by itself. Q sub J, Q sub I. So we're summing over all the other charges in the system. We would have this. And again, we notice that we can factor Q sub J out, because that's not being summed over. Basically, in every single term in the sum, it's exactly the same, just like Q4 here. We could pull it out, so we can do the same thing here. So we pull Q sub J out, we get our sum. And so this quantity here would be the electric field that the jth charge experiences from all the other charges in the system. So a word about units. So we know that the force, of course, has units of newtons. And since basically the electric field is defined as a force per unit charge, it's going to have units of newtons per coulomb. All right, and I'll box this up here. So let's calculate the electric field for the simplest case, which would be a point charge. So electric field So we have a charge here, charge Q. And so we want to know what the electric field is at some general point, let's say R, some vector R away from the point charge, right? So the question is, what is E of R? So we know that if we placed another charge here, basically the force would be given as K, big Q. Let's say we put a little test charge there, little q, R squared, R hat. And again, since our electric field is defined as the force divided by the magnitude of that little test charge that we placed there, it would just look like K, big Q over R squared, R hat, okay? So that's basically the electric field for the point charge. So if we were going to plot out what the electric field looks like from this point charge, so over here, oops, it's not very straight. we would have a series of vectors. So the electric field would be coming radially out from the point charge like this. And then, of course, I'll make the length of the vector roughly equal to the strength of the field, because we see here that the electric field is dropping off as 1 over r squared, just like the force does. Then, the farther we get away, the weaker the field, right? So it would look something like this. So that's basically what the electric field from the point charge looks like. Again, if we wanted to calculate the electric field from an array, oops, let me erase that. All right, all gone. Those were the notes from a little while ago. If we wanted to look at the electric field from an array of point charges, so again, imagine we had one here, let's say it's a positive one, Q1, Q2, we'll make that negative, Q3, we'll make that positive. And so we wanted to know the electric field at some point here, right? We're not putting a charge there. We're just saying, okay, let's imagine, there's a point here. We might put a test charge in there. And so if we put a test charge in there, what direction of the force would it feel? And we always define the test charge as being positive. And so, what we can do then is figure out if we had a point charge in there, what the force would be, and that basically gives us the direction the electric field is pointing in, right? So if I had a little positive charge here, the force from, let's say, Q3 would be, I will call this E3, would point in that direction. From Q1, because this is positive again, would point, let's say like that. Of course, the length of the vector would depend on exactly what the magnitude of the charge was here, and I haven't told you that. But, let's say I knew and I could calculate it. And then Q2, it's negative, so it would point like this. Okay? So it would look something like that. So to get then the total resultant electric field, we would do the vector sum. So for E at P, we would do the vector sum, which would basically be something like this. It would be, E3 plus E1. So we're kind of, again, doing this sort of tip to tail. And then E2, right? So this is E3, E1, E2. This was our initial starting point. This was our end point. So the resultant vector EP looks sort of like that. All right. So EP might have looked something like this. And so algebraically, how does that look? So we would say, okay, E, electric field at point P, is basically, in this case, E1 plus E2 plus E3. Or more generally, if we had, a whole bunch of charges, we would just sum over the electric field from all the charges E sub I. All right. And again, the form for each one of these individual components of the electric field would look something much like what I wrote up at the top here. So for instance, when we are looking at, for instance, the force on Q4 in this earlier example, we factor out this Q4 here, and then we had all these these individual terms here. So these individual terms are basically the same as the individual terms here, just written out explicitly. So when we actually have to calculate, let's say, the electric field at this particular point over here from this charge here, one way we could do that if we wanted to do it in Cartesian is we would just basically, get the coordinates of this point here, the coordinates of that point there, and basically, figure out the position vector. So it would be basically, r of this point minus r of that point. This is basically following the exact same procedure we did in the last lecture video where we were looking at calculating forces. So you basically follow that exact same procedure, except you don't, put in the test charge, the charge over here. You just do that exact same calculation. If you had more than one charge like we do over here, you would just basically repeat that procedure. So for each one of these pairs, you would calculate the vector, for instance, this vector here, I'll call that R3. This vector here, R1. And this vector here, R2. So you'd have to calculate each one of these, and you could do that, for instance, in Cartesian. In your reading exercise that you'll do after watching this video, basically we'll take some example where we have some charge at some position Q, some other position P where we want to actually calculate the electric field, and we'll ask you to do that in Cartesian. So you can basically do it exactly the same way that you were calculating forces. So now I'm going to talk about drawing electric fields. And so we saw the earlier example where we had the positive point charge, and we basically said, okay, well, the electric field from the positive point charge looks like it's going radially out, right? So it looks like a bunch of spikes coming out of the charge. And this is what's called a vector field, right? So a vector field means that at every point in space, there is a little vector associated with that point in space whose direction and magnitude tells you in which direction the vector field is pointing and how strong it is, right? So here we have, let's say at this point here, the length of the vector tells you, the field is quite strong and it's pointing radially away from the point charge. Here it says, okay, at that point it's still pointing more or less in the same direction, but it's a little bit shorter, so it's not as strong, right? So in analogy, I can do the same thing for the negative point charge, and hopefully you can guess what it will look like. It'll basically look kind of the same, but inverted, right? So in this case here, pretty much operationally, it's still radially, but it's radially inwards as opposed to radially outwards. So it looks something like this, right? And again, these vectors get shorter the farther we go out because, again, the strength is still going down, right? So then out here, they're even shorter. This is kind of a pain to draw. So this is usually not how we actually draw the electric fields. How we actually draw them, I'll show you in a second. So let's imagine we have a collection of, well, let's say a pair of charges. So let's say we had two positive charges. Which looked something like what we had up there. So we had one positive charge here, one positive charge there. We'll say same magnitude or same charge. And we wanted to know what the electric fields look like. All right, so what we could see here is that, so let's take some point, we'll say over here. Okay, So this charge here is going to be pointing, there's going to be an electric field from this one that's kind of pointing out that way. This one is going to be will also produce an electric field, which is pointing out this way, but it'll be a little bit less because it's further away. So the vector sum of the two would look like mostly like this from this one here. It would be kind of like, but so it would be kind of like maybe something like that. Okay. And then, let's say over here, well, they're both pointing outwards in the same direction. So there's one electric field from this one will point this way. From that one, it would also point that way, but it would be a little smaller. So maybe we would draw the electric field like this. If we looked over here, we would get pretty much the same thing, except that vector would be bigger. So you can see that this vector would sort of connect, if you will, to sort of that one. So we would get, if I sort of drew a whole bunch of series of vectors, could sort of connect them, right? And so we were going to draw these so-called electric field lines, which is basically like if I drew a whole bunch of vectors and sort of connected them up together, what kind of path would they take? All right. So, for instance, here I would get an electric field line going out like this. There would be one kind of going out like that. What about over here? So if I picked a point sort of just a little bit to the right of this charge here, okay, well this charge would want to have an electric field pointing out that way. This one would want to have an electric field pointing in the opposite direction, but this one, because it's further away from let's say a point over here, would be smaller. So, maybe we would get something that points out this way a little bit. But what about at the center? So right between these two charges, right exactly at the middle, this charge would want to have an electric field that way. This would have an exactly opposite electric field that way, so there would be no field right in the middle. So this, there wouldn't be anything here. So what you can kind of see is that, if I, let's say now picked a point over here, if I picked a point over here, this charge would, point out this way. That would point out this way a little bit. It would point out sort of like that. And so if I sort of connected a whole bunch of points, I might get something like a field line that looked like this. Another one that looked like that. There would be an analogous one going downwards. And so what these field lines actually are is that if I basically look at any one of these points on a field line, exactly tangent to the line is the direction in which the electric field is. So if I looked right here, the electric field would basically be pointing exactly tangent like that. At this point here in space, it would be exactly tangent, so it would be pointing out like this. So this is just an alternative way to drawing these individual vectors, which can be a little bit tedious. So if I was going to draw a whole series of them out, they might look something like, like this. These ones would look more or less like just coming up from the point charge, but these would start to curve a little bit. And I apologize for the lousy artistry, but it's a little bit hard to write with a stylus. So the electric field lines would look something like this. Okay, so they would be basically all be pointing outwards from these two charges. Right in between in the middle of the two charges, there would be no electric field, but there would be a pretty high concentration of field lines. And so so again, a couple things about the electric field, the electric field lines, okay? So these are electric field lines that we're drawing. So a couple things. So first of all, well, I would actually say instead of at, on any field line, the electric field is tangent to every point on the line. So for instance, if I was going to ask you, what does the electric field look like, I don't know, at this point right here, you would say, okay, well, here's my line curving out, so basically my electric field would look, well, pretty close to straight down. Okay, so if I called this point, I don't know, point A, E sub A would look like this. If I was going to ask you what the electric field looked like at this point here, I'll call this point B. You'd say, okay, well, my line is curving like that, so basically exactly tangent is sort of like this. So I'll call that E at B, okay? So basically just tells you in what direction the field is pointing just by going tangent to the line. So that's number one. Number two is basically that if we, this is telling us direction, but doesn't tell us the strength. So can we infer anything about the strength of the electric field from the field lines? And the answer is yes. So basically the density of field lines is basically, I wouldn't say exactly proportional, but it basically indicative, it depends on how you draw it, of the strength of the field. Right. So for instance, we know, in sort of 1 over r squared, we know that basically when you get very, very close to a point charge, the field is very, very large because it goes as 1 over r squared. So when we're very close, for instance, close into one of the charges, you can see there's a lot of lines here, right? There's lots of lines coming out. So we know that the strength of the field around here is really, really big. But if we go out here and we draw sort of the same size dotted circle, we only see sort of one field line that I've drawn sort of intersecting, right? So there's basically, in close to one of the charges, there's a lot of field lines, right? Or even out here, there's a lot of field lines. That means the field strengths are big. When we get out far away, like over here, or let's say out over here, we just don't have a lot of field lines. They're basically all starting to diverge from one another. And you could say, well, what if I drew twice as many field lines? Yes, there would be, twice as many lines penetrating this little dash circle, but there also would be twice as many lines penetrating, a circle here. So, even though the absolute number of lines doesn't matter so much, in proportion we want to know where the field line's most clustered versus where are they sort of most sparse. And obviously the further we get away, the sparser they are and the weaker the field. The closer in, the more clustered, and the stronger the field. So that's basically how to interpret field lines. So one, on any field line, basically when we, if we want to look at any point, we want to figure out the field, let's say at any given point, we look basically tangent to that field line or some other, you could imagine some adjacent field line to it. You just sort of, interpolate. And then the density of the lines basically tells us what the strength of the field is.